Good afternoon. So we start the final session of today with Abhijit giving us a talk on vector space of conformal field theories.
Thank you very much for inviting me to such a nice meeting and having me present my work here. So today I'll talk about some structural results on the space of conformal field theories, or more appropriately, the space of solutions to the conformal crossing equations. In particular, I will show that the vector space of CFTs that are not necessarily unitary and have an abelian symmetry is a vector space. Sorry, the space of CFTs that are not necessarily unitary and have an abelian symmetry is a vector space. This is the work done in collaboration with Indranil, who is a student at TIFR. Okay, so let me begin with some motivations. We know that the crossing symmetry of 4-point functions in conformal field theory imposes extremely strong constraints, and they are so strong they are usually thought to be sufficient to constrain the entire conformal field theory. In fact, even though there are infinitely many crossing symmetry equations that CFT obeys, when supplemented with unitarity, even a single crossing equation is quite powerful. But in the usual conformal bootstrap approach, one looks at a single or a few crossing symmetry equations and gets a very strong, gets either the exact spectrum of the CFT or exact OP coefficient of the CFT in some controlled approximation, or even numerically fix, let's say in the case of, for example, the Ising model, fix the dimension of the first few local operators. Well, this is a priori quite surprising that even, please.
Sorry, so I think in 2 dimensions it's not quite true that this is sufficient.
Yeah, so I will make a comment on that, yeah. Indeed, it is not sufficient in general, and I will say a few words about it. But even in the cases where it works, it is unclear why it works. In particular, there are infinitely many crossing symmetry equations. Why is it that the solution of a single crossing equation should survive when we consider multiple crossing equations? Why is it the case that a given solution always uplifts to a full solution of the theorem? Well, this is not the question I will address, but I will consider another case where the conformal crossing equation is not supplemented by unitarity. In this case, of course, the constraints coming from considering the crossing symmetry of a single 4-point function are extremely weak. In other words, it's extremely easy to write down crossing symmetric 4-point function of, let's say, 4 identical scalar operators, if you don't worry about their conformal block expansion having positive coefficients, which is the signature of unitarity. I hope you all believe that, otherwise I can just even write a function very quickly. It's just a matter of considering a function of, let's say, eta1, which is x1.x2, x3.x4, eta2, which is x2.x3, x1.x4, and similarly eta3, which is x1.x3 and x2.x4, and writing a function f, a symmetric function of f, which is a function of eta1, eta2, eta3, with some fixed degree. And this function will give you, will always give you a crossing symmetric function with appropriate conformal dimension for external scalar operators. But of course, if you do a conformal block expansion, its coefficients the coefficients will not be positive in general. So this is a case where if you don't impose unitarity on a single or a few crossing equations, you are getting a result which is extremely weak, and in no way does it uplift to a full-fledged non-unitary conformal field theory. So what would you have to do if you want to classify CFTs that are not necessarily unitary? Well, one would have to solve all the crossing equations. Now, that seems like a difficult task, but I will show in the talk that it can indeed be accomplished, but with a slightly different formulation of the conformal field theory. That is to use the conformal data, which is not the conventional one. So conventionally speaking, we think of conformal field theory being defined by its 2 and 3 point functions, which obey the crossing equation. Instead, I will formulate the crossing or the constraints of the crossing equation in a slightly different way. And in that way, it will turn out to be relatively easier to solve all the crossing equations. Again, the unitarity is not going to be transparent in this approach because the motivation is to constrain the space of general conformal field theories, not necessarily unitary ones. Okay, so this relates to Matthias's comment. So indeed, although it is usually believed that the solutions to the conformal crossing equation are sufficient to define conformal field theory in 2 dimensions, for example, they are not unique. And a priori, one could even believe that in higher dimensions also, there are other constraints. So in 2 dimensions, for example, in addition to the crossing equation, one requires the spectrum to obey modular invariance, that is the consistency of the theory on a manifold that is not conformally equivalent to, let's say, S2. So similarly, one would imagine even in higher dimensions, there are constraints coming from consistency of the theory on manifolds with interesting topology. That is an interesting problem, and this is not the problem that I will address here. But nevertheless, when I say CFTs, I will just take it to mean the solutions of the crossing equations. Okay. So how is it usually defined? The CFT, as you know, is defined in terms of its spectrum of local operators and their correlation functions, and conformal symmetry allows you to compute higher point correlation functions using just 2 and 3 point functions. And these 2 and 3 point functions, we usually call them the conformal data because the rest is fixed in terms of them. Of course, such a data has a constraint, that is, those are the infinitely many crossing equations that the 2 and 3 point functions obey. That essentially has to do with the fact that in order to construct higher point functions from 2, 3 point functions, one is gluing them, and there are multiple ways of gluing them, and all ways should produce the same higher point function. So in particular, for 4 point function that should work, and if that works for 4 point function, it also works for higher point function. Okay. So instead of that, I will work with a different sort of conformal data. I will show that this data is equivalent to the previous data. So instead of working with the 2 and 3 point functions of arbitrary local operators, I will work with n point functions of a chosen scalar operator, of a single chosen scalar operator, which I call phi. And I'm including all n point functions of it. Now clearly, this set of data can be constructed from 2, 3 point functions by sewing them together. Moreover, if one takes appropriate OP limit, then any 2 and 3 point function of any desired operators can also be obtained from starting with a sufficiently high point function of phi. For example, let's say one is interested in getting the OP coefficient of 3 operators O1, O2, O3, and let's say they are all belong to some symmetric traceless representation of the rotation group. In that case, what one would do is to start with a 6 point function of phi and take a sequential OP in the way that is denoted here. And from this OP, one would read off the coefficient of the 3 point function of O1, O2, and O3. Now, instead of traceless symmetric operators, if one is interested in operators that transform in a more complicated representation of the rotation group, then you would work with a sufficiently high point function of phi, but at some point you're guaranteed to get arbitrarily complicated representations. So in that sense, the conventional conformal data is also encoded in the alternate conformal data that I just proposed. Now, of course, all these data obey constraints. I just pointed out that the conventional data obeys a constraint coming from consistency under sewing, and that is the crossing equation. So similarly, there is a constraint on the data that I proposed, which is the endpoint function of phi. Namely, there are many OP channels that give you given a desired three-point function of desired operators. And all those OP channels should give the same three-point function. So that is the non-trivial constraint that these endpoint functions of phi should obey. So if one wants to solve for, yes, please.
But couldn't there be just many different operators of the same symmetry structure? I mean, why are you saying it results in the same operator? I mean, you could.
Degeneracies?
Yeah, but there could be simply multiplicities arising. I mean, there could be more than one. There could be multiplicities of operators transforming in a specific representation of the rotation group. Of the rotation group. Of the rotation group.
No, but when I do the OP channel, I can isolate a operator of a particular dimension also by looking at the singularity structure. So in that sense, even though there are many operators transforming in the same symmetry, same representation under the rotation group, if I look at appropriate OP singularity of appropriate kind, let's say, if I take I guess.
No, but couldn't there be, say, two operators that have the same symmetry under the rotation group and the same conformal dimension?
So you're talking about the degeneracy.
Yeah, there could be degeneracies, and
so
it may not.
I am assuming here that all degeneracies come from symmetries, some hidden symmetries. So for now, let me assume that there are no other symmetries apart from the conformal symmetry.
Because I think you can write down a set of relations the endpoint functions have to satisfy, which would define for you a consistent CFT, and you would just find out how big the spectrum is by seeing how many different channels. I mean, how many different operators you generate recursively, right? I mean, it would also define a consistent CFT, wouldn't it?
What would define it?
I mean, if you're not assuming that there's only a single operator with a given charge with respect to the rotation group and the conformal dimension, if you allow for arbitrary multiplicities, wouldn't this always lead to a conformal field theory? It just has a different spectrum than the one you had originally in mind.
No, so for now I'm not making assumptions about the spectrum at all. So it could have many operators. So indeed, so that's the kind of consistency condition that I will formulate. The condition which says that these endpoint functions should be consistent under factorization. And then I will construct such endpoint functions.
Okay.
Okay. So the constraint on these endpoint functions is that they should yield the right three-point function, or the three-point function that you want in a unique way. Now, in this way of expressing the constraint, it is difficult to deal with. But it turns out that this constraint of well-definedness of the three follows from even a simpler constraint. And I will show that this simpler constraint is the constraint that if you factorize any endpoint function of phi in a channel which gives you lower point functions of phi, and this factorization is consistent, that is to say that the lower point functions of phi that you obtain are elements of the set that you specified, then you will be always guaranteed to get a unique three-point function. I mean, a three-point function that is uniquely defined. So in other words, this constraint, which looks like a slightly daunting constraint, is equivalent to a constraint that one can work with. That is a constraint which says that the endpoint function of this chosen operator phi should be consistent under the set of endpoint functions should be consistent under factorization into itself. So in this way of writing the constraint, one doesn't invoke any other operator of the CFT, but just works with this operator phi that I've chosen. And now I will show why this is true. That if I assume that the endpoint functions of phi just factorize consistently into lower point functions of phi, then why is it that any three-point function is uniquely fixed? It's a scalar. Yeah. Sure.
Like all CFTs have.
Yeah, if you have a spinning operator, if you take its OP with itself, you in particular have an identity, and because the symmetry doesn't prohibit it, a scalar would appear. I mean, unless there are other new symmetries that are in the game. So any channel which will have identity will have scalars. Okay. So in order to show that any 3-point function is uniquely defined, let me first show that the correlation functions of this form are uniquely defined, where these correlation functions are essentially a bunch of phi's with a single operator of a different kind. So I started with n-point functions of just phi, but from them I will show that such a correlation function for any number of insertions of phi and any O are uniquely defined. And I'm just denoting this correlator in this way. Okay. So in order to do that, let me first define a notion, n minimum, which is the minimum number of phi's that are necessary for this correlator to be non-zero. Okay, so that takes care of the Lorentz transformation properties of O, for example. If it is very complicated, then n minimum would be high. Okay. So now let me first define what that correlator is, that particular one where n is equal to n minimum. And in order to define that correlator with just n minimum insertions of phi, I will start with a correlation function of phi, which is 2 times n minimum point. And I will take that correlation function where I've inserted 2 times n minimum number of phi's at various points. I separate these insertion points into 2 groups and take them apart by distance r and take r to infinity. Now this is a factorization channel, and so more concretely, I'm considering a 2n minimum point correlation function of this kind, where this group is the same as this group but just shifted by r, and now I'm taking r to infinity. And in this channel, if you observe the term which goes as r to the power minus 2 delta O, that is the channel in which there is an O appearing. So if one draws a figure, it would look something like this. From there, what would multiply this r to the minus 2 delta O term is the product of the correlation function appearing on this side and this side, which is just phi minimum O and phi minimum O. And from here, I'm defining what I mean by this correlator, which is phi n minimum times O. Okay, so now this helps us define the correlator of this kind where n is n minimum. And now using that definition, let me define, yes please.
But this is not necessarily the leading term, is it?
It's not a leading term.
So how do you subtract out the descendants of the lower order terms that contribute also in this channel?
Well, I just choose to look at this particular power of r.
But this O operator is then some combination of some primary plus some derivatives of some previous operators and so on, because everything that contributes to that order will have all sorts of contributions, right?
Only if it is integer separated, right? Only if it is integer separated from some other primary. So that also is a statement of degeneracy. Okay. Yes. Yeah, descendants can come and interfere with this.
And so then you're saying this operator can mix with them? Or?
Yeah, a priori it could mix, or it would be difficult to entangle this, unentangle this piece from the descendant piece. I mean, actually, technically speaking, it is not, because you can track down the primary that is contributing to that descendant and take into account all of its descendants by hand, and in principle, one can just remove that contribution. It would be hard to do in practice because one is working with high point function, but at the 4-point function level, we certainly can do it, and we usually do it.
Abhijit, sorry, maybe I missed in the beginning, but these phi's you're fixing once and for all.
Yeah, once and for all. Exactly.
Then you want for any O in the theory, you want to find n minimum, but is that always guaranteed that n minimum there will be a finite n minimum? I mean, for some selection rule reasons.
Yeah. So for now, I'm assuming for now I'm assuming there is just conformal symmetry. But even if there is, let's say, a discrete abelian symmetry, then also this is true. Perhaps what you're...
Flavor symmetry, I was thinking that the phi's would be transformed in some symmetric representation. And if O was an anti-symmetric representation or something like that, then you would not probably find any n minimum O.
So, okay, let me think about the general case a little bit.
I mean, in general, you just produce whatever you can produce out of phi's, but your theory may contain other stuff which you can't produce out of phi's.
Yeah, so that's why I was asking whether...
And in some senses, you can define O in that way as the stuff that appears in that pole inside what you've made out of the phi's.
Yeah.
Right, but I thought he wanted to say something stronger, that for any given O in the theory, you want to try to...
So in some sense, I'm defining the theory in this way. So whatever I get, it will definitely be a solution of the crossing symmetry equations, but if there are selection rules, it will end up capturing a subsector of the theory. Let's say a subsector that is secretly gauged from the original theory. The way, for example, the ON model, we just look at singlets.
Closure is what you're assuming that by itself will be a closed CFT satisfying
crossing equation.
Crossing equations, and hopefully, okay, all right.
That's right. But now, so for now, I have in mind just a case of a CFT with a discrete abelian symmetry, because that's what I will use later. But if you have more symmetries, then what you are saying is the case where you just what you generate is essentially what is generated by this algebra of phi's. Now, for example, that's right. So one comment would be that if there is a U1 symmetry, say, and phi is charge 1, then you will not be able to produce neutral operators, right? If phi is charged under that U1, then you will not be able to produce neutral operators, right? So in that case, you can also work with the slightly, phi bar, the correlation functions that involve same number of phi's and same number of phi bars. And even then, this type of argument will go through. But I will stick for now with the correlation functions that are generated just by phi. Okay. Good. So now, once I have the defined what I mean by correlation function of this kind, where n is equal to n minimum, let me define this for general n. And the way I do it is that instead of considering 2n minimum point function, I consider n plus n minimum point function and take this to be very far. And whatever I get here, I divide it by n minimum of O, and whatever is left would be my definition of a general correlator of this kind. Okay. Now I'm of course not done, because now comes the difficult part, in that I have to show that these definitions are unique. Because there are other ways in which I could get these correlators, and I want to show that those ways also produce the same one. What are these other ways? Well, that is easy to see. Those ways essentially start with an n plus m point function of phi, where n and m, neither of them is n minimum. And from it, when you take a decomposition of this kind and read off this term, you will get the correlation function of n phi's and O and m phi's and O, and they better be what you started off, what you defined them to be. So the way it will work, the way this would be the same, is the following. Because n and n minimum, n and m, neither of them is n minimum, both are greater than n minimum, there exists a phi decomposition channel like this. So I can pick m, let's say, which is greater than n minimum, and I take this block and decompose it in the factorization channel where there is a phi that appears. This is guaranteed to exist because this is non-zero and this is non-zero, so this channel is guaranteed to exist. Please.
There's just one operator O with the corresponding transformation properties. Because if there were two, then they could have different operator product expansions, and you could previously you would see some sum, and yet now you would see some different linear combination.
Sorry, you're saying degenerate? Or
I mean, here you're assuming that there is a single operator O that you produce by taking n minimum phi's in the appropriate limit. If there are three of them with the same transformation properties under the global symmetries and the conformal symmetry, then this factorization wouldn't necessarily have to happen because previously you only saw the correlators.
You're pointing out there could be degeneracies.
I mean, there could be multiplicities of operators being characterized by conformal dimension and the discrete properties. Yeah. And for them, you wouldn't necessarily be able to conclude that.
That's why I'm just limiting myself to theories with just discrete or just abelian symmetries, in which symmetries will not result in degeneracies.
But there may still be degeneracies in the theory produced by I mean, you're starting with a field and you're looking at everything that's produced by this field. So how can you be sure that you're not producing three operators of conformal dimension, whatever, transforming into symmetric representation of whatever global symmetry you have in mind?
I mean, usually the reason for degeneracies is some symmetry, right? Some additional symmetry.
Right, but I mean, here you're making the assumption that there is no degeneracy here. I mean, it may be a good assumption. I'm just saying, if you're not assuming that, then you can't conclude that.
I agree. I mean, the assumption is that all multiplicities of the same quantum number or degeneracies, they are coming from symmetries, and I'm assuming that there is only abelian symmetry. So that's why. Once I look at so that results in a unique operator which will have a given delta and given rotational quantum numbers or transformation property under conformal group in general. Okay, so what I'm saying is that you can take, for example, this piece here and decompose into a channel with a phi, and because my assumption is that in phi channel factorization, my set of correlators is consistently defined. If I cut it here, I get a smaller point function of phi. In fact, I get a function which involves n and n minimum. So from here, it is clear that whatever this block is the same as the one that I defined, because this is same as this that appears in a smaller point function of n and n minimum, which was the definition of this block. I mean, this correlator, phi, 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 and O. N pi then O. I hope this is clear. Similarly, if one wants to show that this correlator here is also the one that is defined, you just do the same thing but on this other side. So from these arguments, one shows that correlators of this type, general correlators of this type, with a bunch of phi's and any different operator with any number of phi insertions are uniquely defined. Okay, now we turn to the question of 3-point functions. So I want to be able to define 3-point functions of any three operators in a unique way, O1, O2, O3. The way I do it is first I start with the definition the way I did it in the previous case, and for that I start with so each O1, O2, O3 will have corresponding n minimum, and I start with the n point function of phi that is just the sum of n minimum. That is to say, a smallest point function of phi which is guaranteed to give me the desired 3-point function. And if I take this particular OP limit, so even though this is slightly fast, you can think of this as a sequential OP limit. That is to say that start from this n-point function of phi, and then you separate out this piece so that you get just the correlator with the O1, and that you can take these out so that you get the 3-point function that you want. And because this n minimum, this piece here is uniquely defined in the previous slides, I can do this and define this 3-point function also. In this way. Now the question is, do all factorization channels produce the same correlation function, produce the same 3-point function? Okay. So in order to do that, let me start with the general point function of phi with a particular OP limit which has O1, O2, O3 in it, and I want to show that whatever this number is the same as the one defined on the previous slide. Now this I proceed inductively. So I assume that up to certain n, the OP expansion to give this 3-point function agrees with the 3-point function that I obtained before. And now I show that you get the same 3-point function even if you start with a higher point function of phi. So for example, this n1, n2, n3, one of them at least is greater than n minimum, because if it were not, I would be back in the previous case. So let's say without loss of generality, n1 is greater than n minimum. So now if you do this, then what one would have to show is that if I take this away and if I consider this factorization channel in which I'm getting a correlator of a bunch of phi's and an O1, should be the same as the one that one gets from a lower point function of phi. Then if that is the case, then in an inductive sense, you can show that whatever are the factorization channels that are taken later would agree with the one that are taken in the lower point function of phi. Is this clear? Maybe it was too fast. Yeah. Yeah, so let's say I'm interested in the 3-point function of some operators O1, O2, and O3. So I want to start with the smallest point function of phi, which will have this 3-point function appearing in some factorization channel. And what is the smallest phi, smallest number of smallest n which will have that? Well, that would be just the sum of n minimums associated to all the 3 operators. And if that is the case, then this is the only factorization channel in which I can recover O1, O2, O3, and that's my definition of O1, O2, O3. And now I want to show that even if I started from higher point function of phi, I get the same answer. And that I proceed inductively. So I assume that at a certain point, till a certain point function of phi, this factorization goes through and I obtain, all factorizations starting from that particular, let's say, n point function of phi. So let's say all ways of getting O1, O2, O3 from n point function of phi agree, n and lower. Now I start with an n prime, which is greater than n, and try to get the same 3-point function. Okay, so the way I would do it is just consider some, any channel of this kind would give me O1, O2, O3. Now, either N1 or N2 or N3 has to be greater than corresponding N minimum. Because if it were not, then all of them were N minimum, and that would give me just the definition of these guys. So, without loss of generality, let's say N1 is greater than N minimum. Okay. Now, I want to show that from this particular factorization, I get a 3-point function coefficient, and that should be the same as the one that I defined or the one that I get from lower point functions of phi. So in order to do that, I only need to show that whatever is in the box should be the same as something that comes from a lower point function of phi. And if that is the case, then I can do these corresponding OPs later and obtain the same 3-point function. So I'm only interested in showing that whatever is in the box here should be the same as the one that appears for any function with less point function of phi. And that I can do because this is n minimum. So again, I do the same trick where there is n minimum. And the rest here with a phi exchange in the middle, which allows me to show that whatever is in the box is the same one that appears in the smaller point function of phi's and agrees with the one that is obtained from smaller point function of phi's. So from these arguments, one sees that just requiring that the n-point functions of phi consistently factorize onto themselves is sufficient to guarantee the uniqueness or the well-definedness of the 3-point function of any kind. Okay, but now the advantage of that, so as I said, that this is the bottom line, that a solution to the conform crossing equation obtained by a set of n-point functions of scalar operator that factorizes consistently. So this is what I will show, sorry. So for now, we just showed that a set of n-point functions that factorizes consistently into itself produces 3-point functions that are well defined. Now, the advantage of this way of expressing the consistency condition is that it's quite easy to work with. And now I will assume that well, CFT has an abelian symmetry. So I'm not assuming, so I'm discarding the possibility that CFT has no symmetry, no global symmetry, but I want to have a CFT with an abelian symmetry. And let's say, for now, let's assume that abelian symmetry be Zn. And for such theories, I will show that this way of formulating the crossing equations. So mind you, if you are able to construct this data, that means you are able to solve all crossing equations. That's what was showed just now. And now I will construct such solution for CFTs that do have abelian symmetry. In particular, I will construct new solutions starting from old ones, and this operation would be the same as the vector space operation. And it's quite simple to see why that is the case. Let me first give you the answer and show why that is the answer. So for a CFT with abelian symmetry, I choose phi to be a very special operator now. This is a special scalar operator with the lowest conformal dimension. Now that is the leading singularity in that channel. And I also want it to be charge 1 associated to this abelian symmetry. Now, my data is the n-point functions of phi. I'm denoting these n-point functions by Fn. And now let's say if I have 2 CFTs with the same abelian symmetry, and the data is this, so now I'm just again specifying the n-point functions like so, then this solution, the new n-point function, which is some power of the first one times some other power of the second one, is also a solution. And this you can see is just a vector space. If you take the log, that's like adding 2 vectors. Alpha and beta could even be complex. If you, I mean, anyway, we don't care about unitarity, so they could even be complex. Would be, yeah. So CFT has, I'm just writing it this way because this is the most general, vector addition. But you could have just just f. If you could just set beta to 0 also. Yeah, so that's what I will show, that it factorizes into itself.
But locality, I mean, if you pick some fractional power, wouldn't you pick up branch cuts that you weren't there before?
No, because everything is in the modulus.
No, but I mean, if you have some function and you take the square root of it,
Yeah,
then you're saying you wouldn't.
yeah, there would not be.
I mean, in general, you would. It wouldn't be single valued anymore, right? I mean, suppose you have some function of variables x1 up to xn, and it's single valued, and if you take the nth root of it, then you may end up on a different sheet after you come round. I mean, if there's a zero somewhere, you would not expect this to be single valued.
I need to think a little bit because I don't know whether there can be zeros.
I mean, in any case, this seems like a pretty strong family of solutions. I mean, one suspicion you may have is that not all of them will come from consistent conformal field theory. So,
Yeah. So what is a consistent conformal field theory? So
I mean, that you could write down some Lagrangian and
okay, yeah, sure.
So
Sure,
you could be suspicious that maybe, I mean, this is capturing some part of the problem of defining a conformal field theory. But if this is really a solution, then you may worry that.
So the claim would be that whatever this is produces a solution to all the crossing equations.
I know, but I mean, you would still feel that may suggest that crossing symmetry isn't as strong as you said on the first slide. I mean, even in higher dimensions.
Higher dimensions. That is probably true. Yeah. But my aim to begin with was to just understand the space of solutions to the crossing equations, and perhaps once you have that, one can try to impose more constraints on it. So even though the CFTs from this point of view does feel like there could be other constraints in addition to the crossing equations, for unitary CFTs, our experience says that the crossing equations are perhaps enough, at least in higher dimensions. If that is the case, one can try to take these solutions, which is the space of solutions, and then try to impose unitarity in a certain way. That I'm not sure how would one go about doing that. But as a solution to the crossing equations, they are valid solutions. Yeah, exactly. That is correct. So when this alpha is an integer, it is like a tensor product, or rather a symmetric. Well, it's an orbifold of the tensor product, but not by the symmetric group, but rather a particular subgroup of the generalized symmetry group. So if you look at a theory with Zn symmetry, and you take its k powers, then the resulting theory has a more symmetry. It has a symmetry which is semi-direct product of the permutation group with the Zns, a bunch of Zns, right? K Zns, and the Sk acts on the Zns also. And the orbifold that is being taken in this procedure is an orbifold by a particular subgroup of this guy. This is called this Shepard-Todd.
But you're only seeing the untwisted sector of that orbifold, because you wouldn't ever see the twisted sector.
Yeah. Right. Yeah, so unless you supplement it with some other constraints. Yeah.
Continuous families of conformal field theories, you're saying.
Yeah.
In higher dimensions
So
also.
you get a vector space. It's alpha times C1 plus alpha C1 plus beta C2. If alpha beta are real and the things that you start off with are real, then it will. Yeah. I mean,
Be forced to look at alpha beta being
Sure,
positive integers.
But I don't a priori don't know. I mean, how one would impose unitarity.
I mean, even just
Or
analytic
probably in some
properties.
perturbation theory, one could do that.
I mean, even analytic properties of the correlators, I know,
No,
I'll
even
tell you
without,
what is the issue with the unitarity. Yeah.
no, even without unitarity C less than 1, there are discretely many, there are discrete
2 dimensions,
in 2 dimensions.
but those are rational ones. If you don't insist on rationality, there are
okay.
such things also.
For example, you might maybe want, when you look at stress tensor correlators, you might want them to be well behaved in some way, not have branch cuts or something like that. So, because those guys are well behaved. So these guys with alpha not integer will not have that property, right? Because but then stress tensor correlators will have all sorts of branch cuts.
In fact, even an more obvious problem as far as the unitarity is concerned, that appears when alpha and beta are not integer, or just alpha is even not integer. I will just show what it is.
Sorry, but the stress tensor, I mean, you normally demand that the stress tensor has dimension D for a local theory, conserved Lorentz invariant. That would not be generally true
No,
for...
so that would be true. So if you start with theories with stress tensor, you will get a conserved current in there.
But they're
Wrong scaling dimension unless you choose alpha plus beta to be equal to 1.
No, because it's some sort of a binomial expansion, right? So it's only the leading term which gets affected, but the rest is not affected.
But I mean, for example, in the 2D case, if you had the stress tensor 2-point function, it goes like 1 over z minus w to the 4. And if you take to the power alpha, it will go like
I'm sorry.
w to
Sorry.
4 alpha, and then scaling dimension 2, right?
I was thinking of something else. I was just thinking that if you start with a theory where you can control the dimension of the external operator, let's say generalized free field theory or something like that, then you can tune the dimension of the external operator so that you can always have stress tensor in the spectrum.
I have not understood. But if you really take the stress tensor, that does not have the right dimension.
Well, then I wouldn't call it stress tensor. So let me just... Yeah. Yeah.
I see.
But it's not guaranteed to have the right conformal, the right scaling dimension.
No, it will have right scaling dimension, I think. Because you can see that if alpha is an integer, then certainly it does. Yeah. So whatever it is analytic function of alpha. And it's a very simple calculation where you can see that when you expand this in 1 over r, then the dimension of the stress tensor appears as it was before.
Yeah. Maybe I'd just like to make a quick comment. So if you're a Euclidean signature, the Fs are positive, so you can take alpha, beta to be arbitrary real, and this kind of makes sense. But if you go to Lorentzian signature, in general, F will have some 0. So in Lorentzian signature, if alpha is not an integer, you'll get some very weird branch cuts.
Yeah, I guess that's what Matthias said. Yeah. I had Euclidean setting in mind, but if you have, right. Yeah, so of course, I'm not imposing all possible conditions that one could impose on a consistent CFT, but just the crossing equations, all of them. Okay. So now this G, I will show that when it factorizes onto itself, you would get the right correlation functions. So there are only 2 possible ways in which it could factorize into itself. So if you start from higher point function of phi, you either look at the factorization channel with the phi exchange or an identity exchange. Now in the identity exchange, the given CFT has this type of expansion, where this is cluster decomposition. So this is the piece where you have identity plus some higher order pieces in 1 over r. The crucial point is that this is the leading piece in this expansion. And if you have a channel with phi exchange, again, because the choice of phi was such that it has the lowest dimension in that super selection sector, when you do this factorization, again, you see that the phi exchange is the leading piece and the rest is subleading. Now, you just using this these properties that whatever is the factorized piece that appears is the leading piece, you can show that if you take Gn plus m point function and substitute in here, then Gn plus m gives you Gn times Gm in, let's say, the identity channel plus some subleading terms. But the point is that identity channel, this is factorizing the way one wanted. And similarly for phi channel also, one can argue the same. And that's how it is. One shows that this set of endpoint functions Gn is consistent under factorization into itself. And from the arguments that I made earlier, this would also give you a consistent set of 3-point functions, which will solve all the crossing equations. So of course, all the comments made here so far are true, that there are other consistency conditions and so on. And because the crossing equations are formulated in a different way here, it would be nice to see whether imposing different conditions on the crossing equations formulated in this way turns out to be easier or not. So let me end with a few remarks. The vector space operation that I just defined on the space of CFTs, it preserves currents. So if two CFTs have currents, it will preserve them. That the resulting theories will also have those currents. So in particular, the stress tensor, the resulting theory will also have a stress tensor. If it has higher spin currents, the resulting theory will also have higher spin currents. No assumption about the spectrum. So here, of course, what you're getting, it has many operators because what is going on is that when you do this, let's say you start with a 4-point function and take its alpha power, and the way to do this alpha power is to expand in large R and do the binomial expansion. And at each order, you will get, binomial expansion doesn't terminate for general values of alpha unless it's an integer. And that's the source of non-unitarity. Because the coefficients that you are getting at some point will turn negative. When it is integer, it stops there. But not always. At some point, you will start getting negative coefficients, and those will be the operators that are the negative norm operators. So you can think of them as some sort of a 1-cent operator, which when alpha is integer, go away. Their OP coefficient becomes 0. So that's the structure roughly of the spectrum, where you have many operators, and they go away when alpha becomes an integer. So this comment I already made, that if it is an integer, then this could be thought of as direct product conform field theory with divided by, just looking at the singlet sector of a particular subgroup of this generalized permutation group. Now, this is also another observation one can make, which is a very simple one, that unitary theories span a positive lattice in this space. That is to say that if you give me two unitary theories, I can take their integer powers with positive integers, and they will remain unitary, because those again just be thought of as n copies and m copies of the unitary theory. Now one could propose a question like this, for example, whether the rank of the lattice is the same as the dimension of the vector space. Now what does that mean if this were true? So I don't know how to answer this question, but it's a question that one can formulate if one formulates in this way. What does this mean? So if this were true, this means that all the non-unitary theories are fake, in the sense that they are obtained from unitary theories by this alpha beta, by vector space addition. So I don't quite know how one would answer this question, but it's a question that one can pose in this formulation. Okay, I'll stop here. Thank you.
Sorry, if I can just come back to the integer powers. I mean, as Matthias was emphasizing, now you would also have these twist operators, right?
Yeah.
Permutation group.
Yeah.
And how do we know that their correlation functions in general will be sensible? I mean, in particular, if we take now non-integer there might be similar additional operators and so on. Wouldn't there be additional consistency checks for the whole theory?
So, yeah, I think this tries to this more general question of having additional consistency conditions, because it would certainly produce a unitary spectrum which obeys all crossing equations, which is what the conventional bootstrap program tries to do. Now the question, you can ask that question just because those solutions to the bootstrap were found as quotients. But if one doesn't know, one is just doing bootstrap, at some point in the space, you will see these things. So it is indeed an interesting question. What are the additional constraints? So those constraints would be some sort, having to do with modular invariance of types of issues. I mean, the consistency of the theory on some interesting manifolds. But having said that, I think if you just think of this, whatever this is, as subsector of this consistently defined theory, I think it should produce a consistent subsector at least.
So, if alpha and beta are negative integers, then you don't have this interpretation.
No, you would still have this. The orbifold.
Yeah.
Orbifold not. So that's sorry. There should be a positive. Is a positive lattice. It should be a positive lattice. So alpha and beta are positive integers in order to think.
Is there? What is the meaning of the negative integer power theories? Is that?
I tried to make sense of it, but it doesn't seem like. Yeah, they're not unitary.
They don't satisfy the unitarity bound. The scalar doesn't satisfy the unitarity bound, right? Central charge is negative.
No, the unitarity.
No, unitarity he is anyway not worried about.
Then this question you could ask even about what's the implication of all the other non-integer things, because the lattice is only the positive
but
cone.
Integer, if he has an interpretation for the positive integers, you might think the next most complex objects would be negative integers. They are somehow more selected. I mean, they're somehow more special than the arbitrary alpha beta. But it has. I mean, it has even. I mean, if you take sufficiently negative powers, then the correlators would be would not have singularities in general. Assuming you started with an original theory in which there were singularities, and there wouldn't be any short distance sort of. But of course, that's related to the negative integer, negative dimensions. But
I think it's the only leading phi. For example, phi will get negative dimension, but the rest of the operator will still have positive dimension because you just expand it.
If you take very large negative powers, then there'll be a large number of operators. Take a free scalar field to the power minus 1000.
Yeah, I have to think about it a bit.
So,
yeah, I think what Jan was saying was right. You will get it because you take these guys and you factorize it, and so in the intermediate channels, I think he's saying you'll get the stress tensor.
Well, but if you start with something that has negative scaling dimension, I'm not sure you would get a stress energy tensor of the right scaling dimension. Yeah, but their correlators are not negative powers of good correlators. I mean, I'm not saying that there aren't any theories with negative conformal dimensions in a stress energy tensor. But if you construct it that way, I can't see how you would get a stress energy tensor. If you take, suppose you take the free boson with negative conformal dimension and you take the inverse of its correlation function. I mean, then in the cross channels, you would never produce. I mean, you would only get negative conformal dimensions. There wouldn't be a single operator with positive conformal dimension.
I thought about this problem, but I'm not able to reproduce the answer right now.
I can see you clearly will get some negative dimensions because the correlator is going to grow when you take 2 points apart. But I didn't understand the basis for the statement that you get only negative dimensions. Where did it's only a positive part.
X minus y to the power 1000 or whatever. And you just Taylor expand it, you'll get positive powers. X minus y, I mean, or whatever.
Let me try to answer privately.
So can I ask you another question? So if I take two different theories and just with, let's say, alpha and beta 1, then is there some statement about, is that correspond to some way of combining CFTs?
Yeah, so that would also be an orbifold of some kind, I mean a quotient of some kind.
So I could also consider taking a theory and its inverse. I mean, there's the notion of an inverse because you have a vector space. So I have a theory and I have its inverse. And that means that there's a way to combine two theories to get a trivial theory. I mean, I assume the theory where the F's are all 1 is somehow an empty theory, is that right?
Right.
So there's a way to take a theory, I could even start with a unitary one and its inverse, which presumably is not unitary, and combine them to get a trivial theory? So how can I combine two non-trivial theories and get an empty theory? I mean, if it...
I didn't quite understand. I mean, that is how the operation is defined, so that you get an...
But you're saying that would fall out of the orbifold? No, but he said it's always an orbifold if I have two theories and I just multiply them, so alpha. I am. No, first I have the inverse theory. So I have a theory and its inverse. Now I combine them with positive powers. 1 and 1. No, but that's why I'm at, so define G to be F inverse. No, but I asked him if I take two different theories and I just multiply them, is that an orbifold? He said yes. So
that is an orbifold.
Yeah.
And you can get one out of it. Because essentially you end up defining an operator in the new theory whose correlation function is trivial. Correlation function is 1. Why is it important? Oh, that's to guarantee that in the phi exchange, in the channel with the phi exchange also, the term with the phi exchange is the leading one. And that, because of that property, when you multiply these two F's together with some powers and do again the expansion, because of this factorization, the leading term in the G also will factorize. If this were not, let's say, leading, but let's say the charge was 0, so the identity will also appear here. And then you will not get, if you just do this construction, you will not get something that factorizes correctly in the phi channel. Yeah.
And I was a bit confused about what exactly the assumption was on correlation functions of the phis. So you said something about factorizing in the identity or the phi channel.
Yeah.
But what was the precise statement exactly?
So in the beginning, the point that I was making was that if the endpoint functions of phi factorize correctly into themselves, in order to factorize these correlators into themselves, you need to find a channel in which there is an either identity or a phi. So these are the only two ways in which these endpoint functions can factorize into themselves. And if that factorization is consistent, then any 3-point function is well defined. Because any other channel will have that operator now, right? The resulting correlator will have that operator.
Right, so you can extract lower point correlators from higher point correlators by factorizing on an intermediate identity or phi channel. That's the statement, right? Then in this particular picture, so I'm still confused then. So here you, in this blob that you drew, but I think I already did not understand it when you were looking at the correlator of phi to the n with O.
Okay.
Because then you split phi to the n in phi to the n min and some other phis. And then you seem to factorize that on some intermediate phi channel.
Phi channel, yeah.
But why did you factorize that? Because you should really look at that's one contribution to this correlator, but it's not a full correlator.
Right, but the way I mean, the argument was like, 1 second. So I just wanted to show that. So let's see. So let's say I start with this point function of phi, and I want to show that whatever I get here, for example, this guy is the same one that I defined, right? That's what I wanted to show. And in order to do that, I used the fact that n is greater than n min, which allowed me to do this additional factorization. So
No,
but I'm not even touching this.
The additional factorization was something that shows consistency between higher and lower point functions of the phis.
Yeah.
But here
the point of the argument was that that is the only thing that is necessary. So that was the main point of the argument, that you only need consistency in phi channel in order to have consistency in all channels. Because if this works, then whatever is given by this bigger correlator, bigger point function correlator, is the same as the one obtained from smaller point function correlator. Because I'm not even touching this part. I'm just going to show that this part is the same as the one coming from the lower point. In order to do that, I do it this way.
Yeah, I guess I still we can talk about it later.
Sorry, there's a very basic question, but I just got confused by some of the discussion right now. I mean, the whole idea of factorizing into channels relies, in some sense, on the fact you bring 2 points close together, and it makes sense to do an OP. Combine those two.
Or bring.
Correct, but in this situation where you have these negative powers, it's the opposite, right? You separate 2 points a lot, and that becomes the most important term in the correlator, because now you have x minus y to some positive power.
But it's the only the leading power that is going to be changed, but the rest of the powers are going to be still positive, even if you have a negative power.
Okay, but
the sequence in which you are doing this 1 over r expansion will remain the same. You have something like, some number, some correlate, some function, plus 1 over r, let's say, times something. And whatever you do, whatever power you take, will admit a 1 over r expansion.
No, Abhijit, just take a field with to the power minus, take a scalar field or something which has dimension 2, conventional dimension 2, and then take to the minus 2 power, or minus 1 power of that. You'll have something, the 3-point function will look like x12 square times x23 square times x13 square. Now that has a Taylor expansion. If you take 2 and 3 together, it will just have 6 terms or something in the expansion, because it's a terminating
but that's not
expansion.
That type of correlator never appears. So what will appear is this 1 over x12.
No, I was thinking of a 3-point function. 3-point function of primaries, which in the original theory looks like 1 over x12 square, 1 over x13 square, 1 over x12 square times x23.
Okay.
Yeah. And then you take the minus 1 power of that.
Okay.
So then that new fn to the minus 1 will be x12 square times x23 square times x13 square.
Yeah.
But that has just that has no, when you bring 2 points together. Firstly, it doesn't obey cluster decomposition, because that's what it will.
Yeah, but that is gone anyway. Cluster decomposition is gone.
But even in the expansion, it has only finite number of terms.
I'm thinking of expanding these higher point functions into lower point functions. So the 3-point function would just be some
But you can
fundamental
still
data.
look at the OPE from the point of view of the 3-point function, right? Of the new operators. If I understood it correctly, this Fn to the, this particular 3-point function to the -1 power, I should be able to interpret it as a 3-point function of this new theory, right? And in that new theory, there's only 3 terms in that expansion.
Sorry, how are you expanding the 3-point function?
I mean, I take, say, 2 going to 3 in the 3-point function, or 1 going to 2, and then take...
These are just polynomials, right? So you'll get some finite terminating series.
Yeah.
Sorry. So firstly, I don't see how it is...
You're saying you have negative conformal dimensions and the descendants terminate. That's what you're saying. Because there are only 3 descendants of the operator because they're negative conformal dimension. But yeah.
I mean, just having negative conformal dimension should be an issue, right? We know of theories where...
No, but I mean, negative conformal dimension per se is not an issue, but you would typically have an infinite tail of derivatives, and somehow...
Even in the 3-point function? Because I thought Rajesh was pointing out 3-point function.
Yeah, but I mean, if you expand it, then you see the,
You're saying this is maybe you're saying this is a special theory in which...
Some correlators do grow.
In which there are an infinite number of primaries, but they cancel against the descendants.
Descendants, the descendant series terminates because you take
descendants, but there aren't infinite number of primaries in this OPE anyway.
I mean, certainly in 2 dimensions, that wouldn't be compatible with the Versora symmetry. So somehow this wouldn't be conformal. I mean, even letting aside the modular invariance.
Sorry, why is that?
Well, because I mean, the L-1 descendants of some state, they never terminate. I mean...
So, and just one more question about this. The cluster decomposition is clearly violated, right?
For negative powers. I mean,
clearly, but there's no cluster decomposition.
But that is the case with negative dimensions anyway, right? That correlators would increase large distances.
Okay, so it looks like there are no further questions, and if I understand, no announcements also. Okay, so great. So then we'll end for today, and see you again tomorrow. Thank you once again, Abhijit.